Hello everyone, my name is Jiajing and I'm from Singapore Management University. I'm so excited to present the paper, Reinforcement Learning for Zone-Based Multi-Agent Pathfinding Under Uncertainty. As we know, there are a lot of autonomous vehicles in our life, such as autonomous cars, guided cars in the freight terminal, and the drones. It's important to use some traffic management system to avoid the congestion. Our work is motivated by the traffic management system. We want to address the question how to coordinate the movement of autonomous vehicles in a partially observable environment with some uncertainty. In this paper, we have made three contributions. First, we use a general DECPOM-TP framework to model our zone-based pathfinding under uncertainty. Second, we proposed a novel DC programming-based formulation of the policy optimization. Last, we developed a simulator on the Unity 3D platform, which can combine the simulation environment and the learning algorithms. Let's get started with the formulation of ZBPF. We are given a graph where each node is a zone. Two neighboring zones are connected by an edge. We're also given a set of agents with the source and destinations. For example, the first agent should move from S1 to G1. In this problem, we allow zones with capacity of more than one agent. If the number of agents in a zone is greater than the capacity, we say there is congestion. We assume there are minimum and maximum travel time for crossing two zones. The realized time is sampled from a distribution given some constraints. That's where the uncertainty comes from. And our objective here is to make sure that all agents can reach the destinations as soon as possible. Meanwhile, we want to minimize the congestion level. Now, let's look at our simulator. Our simulator is generally enough to represent both 2D and 3D maps. Here we show the movement of 10 agents on a 3D map under random policy. The spheres are the zones and the cubes are the agents. Agents are crossing different zones to reach the destinations. An agent can have different speeds for crossing two zones. Moreover, if a zone is highlighted, then there is some congestion within this zone. If an agent is highlighted, then the agent has reached its destination. Now, let's move to the agent's decision model. First of all, we introduce the states and actions. The state is a tuple of three components. The first one is the current zone. The second one is the zone that the agent is planning to go. The last one is the remaining time for crossing zones. The action is either a hybrid one or just the no-op. Let's look at an example. Suppose an agent is newly arrived in zone 1 at time step t. Firstly, it needs to decide which zone to go. For example, zone 2, 3, or 4. That's the discrete action part. Secondly, it needs to decide the speed for navigating to the decided zone. For example, zone 2. To realize the travel time is controlled by the continuous action nu. We show in the paper the travel time distribution can be modeled by a wide class of exponential family of distributions, such as binomial distribution, Gaussian distribution. Therefore, the movement that we can model is very realistic. Now, let's look at the transition function. We use the exponential family distributions to model the transition function. The family can model uncertainty in a lot of applications, such as navigation task, control task. In our model, We assume partial observability, meaning that agents can only observe the local neighboring zones. Reward function is that every time step t, a negative reward will be given for not reaching the goal. A positive reward will be given for reaching the goal for the first time. Penalty will also be given if the capacity constraint of a zone has been violated. Now we introduce the policy optimization in DC4. We assume a stochastic policy pi for the discrete action and a deterministic policy mu for the continuous action. Then we can get the objective function, which is based on the trajectory sigma. The objective function is non-convex. It's very difficult to optimize directly. Moreover, nonlinear solvers are not able to handle a large number of agents. That's why we use DC programming here. In DC, the convex-concave procedure can be applied to solve it iteratively. By using CCP, we can get a new function. It is much easier to solve than the original optimization problem, because here, the Q functions are fixed with respect to the old policy, and other parts are either linear or concave. When the policy of each agent has a very convenient form, such as a tabular policy, in general, nonlinear solvers can be used to optimize it to get a better policy iteratively. However, when the exact planning model is not very available or the state space is too large, we can use a gradient-based learning approach to approximately optimize it. When doing multi-agent learning, we also need to design some credit assignment scheme to reduce the variance of the gradient estimates. Okay, finally, we will show some experimental results on both 3D and 2D maps. We have tested several instances on 2D maps with different size and different number of agents. For each grid, the starting and the goal locations were the top and bottom rows. The capacity of each zone was sampled uniformly from a range, say 1 to 4. The challenge here is that multiple agents can have the same start or goal zones. Therefore, proper route or travel time should be assigned to them. We compare our learning approach with the credit assignment DCRL with linear gradient-based approach VPG and the multiple agent Q-learning-based approach HA. The figure shows that our approach DCRL can provide significantly better SOC quality than the baseline approaches. The SOC is very close to the solution where all agents just follow the shortest path. Moreover, our approach was quite stable during learning and converged much faster. We also show the congestion level and how many agents were unable to reach destinations in these three approaches. The results show that our approach is able to effectively minimize the congestion level. Meanwhile, agents were able to reach the destinations. We have also generated some 3D maps. The settings were same as the grid. For such maps, our approach DCRL worked much better than the baseline approaches as expected in terms of the SOC, stranded agents, and the congestion level. Okay, finally, to summarize, we addressed the problem of ZBPF and the uncertainty. We have developed a simulator based on the Unity 3D game engine. We presented a novel policy optimization formulation. The formulation is based on the DC programming, which can be applied for both planning and learning. We have also designed a credit assignment scheme, and empirically, our approach worked much better than the baseline approaches. That's all for my presentation. Thank you for listening.